Hello, this is Lab 12 Operational Amplifiers. Figure 1 shows the operational amplifier. It has two inputs and one output. And also it needs to be connected with the power supply. And in some diagrams, the power supply connection is not shown, but in real circuit, it must be included. Figure 2 shows the operational amplifier that we are going to use. There is a notch, and the pin numbers are assigned in counterclockwise order, beginning at the notch. So the pin number is 1, 2, 3, 4, 5, 6, 7, and 8 in the counterclockwise direction. And we will use pin 2 and pin 3 as the input and pin 6 as the output. Pin 4 and pin 7 is connected with the power supply. We will not use pin 1, 8, and 5. For more details about this operational amplifier, you can look at its user manual. And there are some important limitations to keep in mind. First of all is that the supply voltage cannot exceed the maximum rating. And also the current cannot exceed the maximum rating. Usually it's 30 milliampere. So be careful when you use the circuit. And on previous slides, we introduced that number 7 and number 4 is connected with the power supply. And usually we put two capacitors. The capacitors are used to stabilize the DC power supply. What we want to know from analyzing the operational amplifier circuit is that we want to know the relationship between VO and Vin. So there are three steps in analyzing the circuit. The first step is to use the ideal model, which means the input current equals 0 and the voltage at the positive and negative terminal are the same. And second, apply nodal analysis to the circuit. Finally, by solving the nodal equations, we can obtain the relationship between VO and Vin. I will give you some examples to demonstrate the analysis process. Let's take a look at the non-inverting operational amplifier circuit as the first example. And this circuit is shown in figure 4 on our lab user manual. So first, let's take a look at the node voltage. The voltage of this node is obvious. It equals Vin, and the node voltage of this node equals VO. And then we apply KCL on this terminal. Apply KCL. So the current flowing through R1 should be equal to the current flowing through RF. Let's write the equation. The current flowing through R1 equals Vin over R1. It equals the current flowing through RF. The current flowing through RF equals VO minus Vin over RF. So by simplifying this equation, we can obtain the relationship between the input voltage and output voltage. The second example is the inverting operational amplifier. You can find this circuit on figure 5 in the lab user manual. In this circuit, the positive terminal is connected with the ground. So the voltage on the negative terminal should be equal to 0. And we can apply KCL on the on this terminal, apply KCL. So the current flowing into this node should be equal to the current flowing out of this node. So we can write down the equation. So V in minus 0, that is the voltage of this node, over R1 should be equal to 0 minus VO over R2. By simplifying this equation, you can obtain the relationship between the input and output. The third example is the inverting operational amplifier summing circuit. This is similar to the previous example. The positive terminal is connected with the ground, so the voltage of the negative terminal should be equal to 0, and we apply KCL on this node. And let's write down the equation. V1 over I1 plus V2 over R2 equals 0 minus VO over R. So by simplifying the equation, we can obtain the relationship between the input and output. And in the experiment, the most important thing is do not damage the circuit. And in the first experiment, you need to connect the circuit as shown in figure 4. And the operational amplifier needs to be connected with the power supply, and you need to use capacitors to stabilize the DC power, and follow the instructions and record the output voltage as you carefully vary Vin between -6 to +6 in 1 volt steps, and record the data. You need to attach a table in your lab report, that is the input, output, and also you need to write down the actual resistance of the resistor. In the second experiment, you connect the circuit as shown in figure 5, and in your lab report you need to write down the input, output, and also the actual value of the two resistors. The third experiment, you will use the same circuit, but now the input is different. Now the input is from the signal generator, 500 Hz sine wave, and you need to determine the input peak-to-peak voltage in order to get a 4 volts peak-to-peak output. In your lab report, you should also attach pictures showing what the input and output looks like on the oscilloscope. In the last experiment, you need to connect the circuit as shown in figure 7, and V1 is the function generator, and V2 is a DC power supply. You need to adjust the DC power supply and observe the output. The solutions of pre-lab questions will be discussed in another video. That's all for today's lab. Thank you.